Hi, good day. This is Engineer Margisal here, and welcome to the online class for Abstract Algebra. In this video, we will be talking about binary operations. Although the term binary operation may be a new term for us, believe me, you have encountered binary operations already. Oh, nang hindi natin alam. When we are in high school, doing high school mathematics or high school algebra, we have encountered addition and multiplication of numbers or variables. And actually, addition and multiplication are binary operations, and they have the same principle. Addition and multiplication takes two elements to produce another third element by obeying some law. Or addition and multiplication takes two inputs to generate an output. And that is why they are called binary operations. And the word bi, it means two. So they take two elements called the operands to create a third element by obeying a rule or a law. By definition, if S is a set, then a binary operation in S is a function that associates to each ordered pair, for example, S1, S2 of elements of S, an element of S, which we denote by S1 star S2. Okay. Ang ibig sabihin lang nito is meron kang pares or elements ng isang set, sabihin natin S, and then ina-associate mo siya, okay, related siya by a certain rule or law sa isang element pa na nasa S din. Notice yung pagkakasabi niyang ordered pair. Ibig sabihin, may order tayo. Okay. Which means na it is not necessary that S1, S2 is equal to S2, S1. Okay. It is not necessary that S1, S2 is equal to S2, S1 to the ordered pair is to S1. And of course, it is also not necessary that S1 star S2 be equal to S2 star S1 because it is an ordered pair. It may or may not be equal depending upon the property of the binary operation. So the symbol for binary operation is the star or asterisk, but we read it as star, and it denotes any other rule, okay, that is a function which associates two ordered pairs or one ordered pair to other elements of S. So, ibig sabihin, yung inputs mo for S1, S2, for example, magbibigay ng output na S3, okay, which are all in the same set. Ibig sabihin, S1, S2, and S3, para matawag mo na binary operation, dapat nasa same set din siya na S. Okay, I'll give you an example. Addition is a binary operation on the set of positive integers. Okay, if we define the binary operation asterisk A star B be equal to A plus B, then addition on the set of positive integers is a binary operation. Okay, give you an example. For instance, if we have 3 plus 2, okay, 3 is a positive integer, therefore it is an element of the set of positive integers. 2 is also an element of the positive. If we evaluate 3 plus 2, we get 5, which is also an element of the set of positive integers. And because the two elements, the two inputs, and the output are all, or they all belong to the same set, which is the set of positive integers, we say that addition is a binary operation. And we say that addition is closed in the set of positive integers. Yun lang naman ang requirements para matawag siyang binary operation. You take two inputs from the set, then you get an output which also belongs to the same set where your inputs or where you got your inputs. Addition, therefore, is a binary operation on the set of positive integers. However, subtraction is not a binary operation on the set of positive integers. Why? I'll give you an example. If we subtract 3 minus 1, 3 is a positive integer, 1 is a positive integer, we get 2. Yes. Okay, this 2 is still an element of the set of positive integers. However, pag binaliktad natin siya, 1 minus 3, 1 is a positive integer, 3 is a positive integer. What we get? Negative 2. 1 minus 3 is negative 2. And negative 2 do not belong to the set of positive integers. It belongs to the set of integers or to the set of negative integers. And therefore, subtraction is not a binary operation because the output do not belong to the same set as the two inputs. However, subtraction is a binary operation on the set of integers. When we say set of integers, that comprises of the set of positive integers and also the set of negative integers and 0. So, if we have an example, 1 minus 3 equals negative 2, subtraction is a binary operation on the set of integers because 1 is an integer, 3 is an integer, 1 minus 3 equals negative 2, negative 2 is an integer. Although subtraction is not a binary operation on the set of positive integers, subtraction is a binary operation on the set of integers because, again, the set of integers comprises or consists of the set of positive integers, the set of negative integers, and 0. So, negative 2 still belongs to the set of integers. Therefore, subtraction is a binary operation on the set of integers. See? Another example. Okay. Multiplication is a binary operation on the set of positive integers or real numbers or rational numbers. Okay. For example, if we multiply, for example, if we are working on the set of positive integers, if you multiply two positive numbers, okay, on the set of positive integers, if you multiply two positive numbers, you always get a positive number, right? Okay. Therefore, multiplication is a binary operation on the set of positive integers. How about for the set of positive or the set of integers? If you multiply negative 3, an integer, times negative 10, you will get 30, which is again an integer and belongs to the set of integer. If you multiply 3 by negative 5, you get negative 5, and negative 5 is still an element of the set of integers. Therefore, multiplication is a binary operation on the set of integers. How about on the set of real numbers? So, if we multiply any real number, course, we have pi times 2. We get 2 pi. And 2 pi is still a real number. Therefore, multiplication is a binary operation on a set of real numbers. And of course, also on the set of rational numbers. However, on the other hand, okay, burahin ko muna to. Division is only a binary operation on the set of positive rational numbers and the set of positive real numbers. Why? Okay, I give an example. Okay, on the set of positive integers, okay, on the set of positive integers, we may not always get a positive integer as a quotient. So if we divide 4 divided by 2, we get 2. Yes, it is a positive integer. However, if we divide 2 by 4, we get 1 half, and 1 half is not an integer or do not belong to the set of positive integer. Therefore, division is not a binary operation on the set of positive integers. Okay, how about on the integers? Ganun din, no? If we divide negative 4 by negative 8, we get positive 1 half. And 1 half is not an integer. Therefore, it is not a binary operation on the set of integers. Okay. How about on the set of negative real numbers? Why is it not a binary operation on the set of negative real numbers? Because if we divide negative 4 by negative 2, we get positive 2. Positive 2 is still a whole number and a rational number. However, it does not belong to the set of negative rational numbers. Therefore, again, it is not a binary operation on the set of negative numbers or negative rational numbers. On the set of positive rational numbers, yes, when you divide two numbers that are positive, you always get a positive number, right? And since it is a set of rational numbers, integers and fractions and decimals are belong to this set. So on the set of positive numbers or positive rational numbers, division is a binary operation. On the set of on the set of negative real numbers, again, it is the same as the set of negative integers, because if you divide negative 3 by negative 2, you get positive 1.5, and 1.5, yes, it is a real, but it is not a negative real number. So it does not belong to the negative real number, and thus division is not a binary operation on the set of negative real numbers. Thus, conclusion, division is a binary operation on the set of positive rational numbers and the positive real numbers only. Okay. And lastly, division is not binary operation on the set of real numbers or rational numbers. Okay. 0 is still a real number, right? And if we divide 3 by 0, 3 is a real number, 0 is a real number, and the answer is undefined. And undefined is do not belong to the set of real numbers. Therefore, division is not a binary operation on the set of real numbers, because if we divide by 0, we get an undefined result. Same is true with rational numbers. You divide a fraction by 0, it will not give you a rational number, and that therefore makes division not a binary operation. Okay, we have another example. Binary operation is defined by a star b equals a cubed plus b squared plus 1. Is a binary operation on the set of integers, real numbers, rational numbers, set of positive real number integers, positive real numbers, and positive rational numbers. Okay, let's just have an example. Maybe real. If we evaluate a, okay, I'm sorry, a star b, where ra equals, okay, let's begin with real numbers or integers. So if a equals 2 and b is negative 3, we get a star b equal to 2 cubed plus negative 3 squared plus 1, which is equal to 8 plus 9 plus 1. And we get a plus 9 plus 1 be 18. And 18 is an integer. And therefore, yes, the binary operation defined by a star b equals a cubed plus b squared plus 1 is a binary operation on z. Okay, I can prove them one by one by setting an example, but I just want to prove why the set of negative integers is not makes this binary operation, or makes this definition not a binary operation. So let's try it on the set of negative integers, and let a be equal to negative 1 and b equal to negative 2. Okay, so a star b will be evaluated to be negative 1 cubed plus negative 2 squared plus 1. And we get negative 1 cubed is negative 1, negative 2 squared is positive 4, and plus 1. That is negative 1 plus 4, that is positive 3 plus 1, 4. We get a positive integer, and we are working on the set of negative integers, and 4 is do not belong to or is not an element of the set of negative integers. Thus, this example alone, or these values as a b alone, okay, is a contradiction to the claim that z, or that the binary operation defined by a cubed plus b squared plus 1 can be a binary operation on the set of negative integers. Because there is one contradiction, then it cannot be a binary operation. Okay, fourth example. If we let X be some set and let S be the set of all subsets of X, for example, if we let X be the set of 1, then the subset of, or the set of S be equal to the null set, and of course 1, because as we all know, a null set is a subset of all sets, right? And since S is a subset, is a set of all subsets of X, then S is equal to the set of null set and the set of 1. And if X equals the set of 1, 2, then S is the set of null set of 1, set of 2, and set of 1, 2. The operation of intersection is a binary operation. Let's show how is the operation of intersection is binary operation. So let's, okay, this is end, okay. Sorry, typographical error. So let's try this example for this value for set. The operation of intersection is a binary operation on S since A, B are elements of S. Okay. We will be working on this set. For example, this is the set, which is a subset, which is a set of all subsets of X, where X is a set of 1, 2. So we take elements here from set S, and then we perform intersection, the operation intersection, and see if the result is still an element of S. If it's still an element of S, then the operation of intersection is a binary operation on S. So, for example, the set of 1 then intersected with the set of 2, and that equals to, intersection means the common or the set of all elements that is common to both sets. So here we have the set of 1 and we have the set of 2. They do not have a common element, right? Therefore, the intersection is null set, and null set is a subset or an element of S. How about 1, 2? Okay, I'm sorry. That should be intersection. One set of 1, 2 intersected with the set of 1. Okay, again, intersection means the set of all common elements to both two sets. And that is the element common on both sets of 1, 2 and set of 1 is 1. And set of 1 is still an element of set S. Okay, we can go through every other samples, but it is very clear that the operations of intersection is a binary operation on S, where S is the set of all subsets of a certain set X. Okay, sorry, nag-overlap siya. I'll erase it na. Okay, yes. Okay, let's have the last example on binary operation. Okay, before we head on to the example, there is a definition of a 2 by 2 matrix. If we say 2 by 2 matrix, a matrix is an array of elements or objects. Okay. In this example, it's an array of letters, or array of numbers, okay, wherein there are rows and columns. Okay. And it says here, let S be the set of all 2 by 2. 2 by 2 means there are 2 rows and 2 columns. So there are 2 by 2 matrix or matrices with real entries. Thus, an element of S looks like here, AB. Okay, sometimes they use the bracket, sometimes a big parenthesis, but it's the same. This is a matrix, a 2 by 2 matrix to be specific. And let S be the set of all matrices that looks like this. Okay. Where every entry, all entries in the matrix are real. Means A, B, C, and D are all real numbers. And we define a binary operation xy to be the matrix product of x and y. That is, yeah, okay. This is matrix multiplication. When we multiply matrix, this is the formula. 2 by 2 matrix. Okay. For the first entry, okay, row 1, column 1 of the result or the output, we multiply row 1, column 1 times row 1, column 2, row 1, column 1 of the second matrix plus row 1, column 2 times times column 1 or row 2, column 1. So I guess you can manage to look at the pattern, but it's like this. So A times E plus B times G. That is the first entry here. Here plus A times E plus B times row times column. Okay. The next entry, AF plus BH here. A F B H C E D G C F D H. That is matrix multiplication, specifically 2 by 2 matrix, or multiplying 2 by 2 matrices. From those definitions, then we can say that the operation, matrix multiplication is a binary operation on the set of X. Okay, for instance, we have the product of 2 by 2 matrix 1 2 0 1 and 2 1 1 2. The product is 4 1 5 2. How did we evaluate 4 1 5 2? From the formula from the previous slide, we get 1 times 2 plus 2 times 1, that is 4. Okay, next we have 1 times 1 and 2 times 2, that is 1 plus 4, we get 5. Next we get 0 times 2 and 1 times 1, that is 1. Then lastly we get 0 times 1 and 1 times 2, that is 2. And as you can see, 4152 is still a real, the entries of 4 matrix 2 by 2 matrix 4512 are still real numbers and still a 2 by 2 matrix. Therefore, it's still an element of S, and because they are all elements of S, then our operation, matrix multiplication on 2 by 2 matrices is a binary operation. Okay, you can have other examples if you want. You can try negative numbers. You can also try some special numbers, pi and e, but you get a result which is a 2 by 2 matrix with real entries, and thus again concluding that matrix multiplication is a binary operation on S. Just like other operations that we know, we also have the properties of binary operations. We can say that a binary operation is commutative if S1 star S2 is equal to S2 star S1 for every or for all elements of S1, S2 element of S. Then binary operations associative, where S1, S2, S3 are all elements of the same set S. Okay, let's try to have an example. So we have example number one: subtraction on Z, or the set of positive or set of integers, is neither commutative nor associative. Okay, let's prove it. 1 minus 2 is not equal to 2 minus 1, right? Because 1 minus 2 is negative 1 and 2 minus 1 is positive 1. Although the answers on both sides of the equation is or belong to the set of integers, they do not have equal. And for a binary operation to be commutative, they should have equal values, or they should equal. And because they're not equal, subtraction on positive integers, or subtraction on integers, sorry, is not commutative. How about associativity? So if we subtract 3 from the difference of 1 and 2, we get 1 minus 2 is negative 1, and negative 1 minus 3, this is negative 4, right? Negative 1 minus 3, that's negative 4. On the other side, if we subtract the difference of 2 minus 3 from 1, we get 2 minus 3, negative 1, and negative 1 minus negative 1, we get positive 2. And negative 4 is not equal to negative 2. Therefore, subtraction is neither commutative nor associative on the set of integers. Let's try other example. Number 2. Okay, let the binary operation A star B be equal to 2 times to the sum of the inputs A plus B on the set of positive integers. Okay, let's try if it is commutative, of course, because A star B equals to A plus B. And if we try to rearrange, muna naman si B kay A, we got 2B plus A, which is just the same as 2A. 2 times A plus B. Therefore, clearly, it is commutative. But is it associative? Let's try and check. Okay. I have here the inputs X, Y, and Z. Okay. The are Y. Tayo man ito. Dito, let's evaluate first the expression inside the parentheses. Here, X star Y. So, X would be our A and B would be our Y. And A star B is equal to here, 2 times A plus B. Therefore, we get 2 times X plus Y because this is A and this is B. Right? Now, in this let's try to regroup it and evaluate this expression. Okay, again, let's try to evaluate first expression inside the parentheses, y star z. This is our a and this is our b, and a star b means 2 times a plus b. Therefore, we get 2 times y plus z. Okay, again, distributing 2, we get x star 2y plus 2z. Again, this is a star, and this will be our new a. 2y plus 2z will be our new b. And a star b would give us 2 times a plus b, where our new a is x, our new b is 2y plus b. Okay, and distributing 2, we get 2 times x 2x, 2 times 2y 4y, 2 times 2z 4z. You can see when we regrouped it, clearly 4x plus 4 plus 2z is not equal to 2x plus 4y plus 4z. Thus, the operation, which is defined by a star b equals 2 times a plus b. Okay, other variables. Kagaya nga dito, ginamit ko si a plus b pa rin. No, nagle-let pa rin ako ng ab para kapag ina-apply natin siya sa formula, hindi tayo nanilito sino or ano ang katumbas ng a at ni b based on sa give. Okay, let's have another example. So this time naman, yung binary operation natin na a star b, ang ibig sabihin niya naman is 2 times a times b on the set of positive set of integers, sorry. Lagi ako nagkakamali doon. Okay, let's try. Commutative siya, of course, kasi pag pinagbaliktad natin, b star a, ang lalabas na nasagot natin is 2ba. And because this is multiplication, we can rearrange it and 2ab. Clearly, equal lang siya sa a star b. So, commutative siya. Pero, is it associative? Let's try to find out. So, try natin to. X star y, then quantity x star z. So, unahin natin yung nasa loob ng parenthesis. Si x yung a natin, si y yung b natin. And a star b, by our definition, is equal to 2ab. Therefore, we get 2xy. Kasi nga si x yung a natin, si y yung b. And then, we get 2xy star c. So, this time, 2xy, siya na yung bagong a, si c, siya na yung bagong b. And what happens if we star a and b? We should get 2 times a times b. And since a equals to xy dito sa second equation, then and b is equal to z, then we have 2 times the product of 2xy and z. And simplifying it, we will have 2 times 2, 4 times xy and z. Yeah. Okay, let's try to regroup naman. And let's see kung parehas yung lalabas ng sagot. So, what if ganito naman? So, unahin mo pa rin nasa loob ng parenthesis, si y ang a natin, si z ang b natin. And a star b means 2ab. So, 2ab means 2yz. Kuha. Then next, ito na yung magiging bagong b natin. Si x na yung magiging bagong a natin. And a star b means 2ab ulit. A, b. So, x is a, and b is 2xy plus c. And if we simplify it, we get still for x, y, z. Since parehas po yung nakuha natin nung niregroup natin sila, then we can say that our binary operation is associative. Okay. I have here, oh my god, bumalik siya. 1, 2, 0, 1 times 2, yan, is hindi parehas pag binaliktad natin. Hindi magiging parehas yung sagot. Therefore, matrix multiplication ng 2 by 2 matrices are not commutative, pero associative siya. So, I will left this example for you to explore, pero it should be associative but not commutative. So, that's all for binary operations and yung mga properties ng binary operations. For questions or clarifications, feel free to contact me, message me, DM me, or comment po tayo sa Google Classroom. And hope meron tayong natutunan. Thank you for listening and happy learning.